Okay, so as a review of the last couple of weeks about witness sets function in numerical algebraic geometry as a way to compute with and study positive dimensional varieties. Before this, all we've done is really talk about zero-dimensional varieties, and witness sets are a way to massage a positive dimensional situation into a zero-dimensional situation. Namely, you just slice with a bunch of hyperplanes until you have finitely many points, and now you're back at the problem you do know how to solve. Standard math trick, right? I don't know how to solve this, massage it until it looks like something I do know how to solve. And when we began, we said a witness set was a triple. So first of all, a witness set for what? Well, some variety is a triple. X is a union of components of the event. I guess I should say that this is equidimensional. So it may not be reducible, it may have lots of components, but all those components have the same dimension. And so what do we need? Well, the first thing we need is we need a polynomial system which cuts x out. And we're going to remove a constraint on ourselves by saying we don't need f to cut x out perfectly. We just want f to cut out the components of x. That's enough. If f cuts out extra components, who cares? I just want the components of x to be components of the event. L is numeric linear space of complementary dimension, and S is approximations of L intersections. Okay. So for example, that's a good circle. Okay, let's do that. Might have a variety. Looks like this. Okay. That's a variety you might care about. And so now, equipped with this definition, we talk about a witness set for, let's just say the union of this surface and this surface, or we can talk about a witness set for this surface, or we could talk about a witness set for the union of these two curves, or a witness set for these 2 points. Think about what a witness set for points would be. It's kind of a trivial thing. It's just finding the points, really, because the complementary dimensional linear space is the whole space. Okay, but so far we don't really have a gadget which encodes all that information for all the components. Okay. And indeed, this variety, we're going to write it as a union. Say of components in this way. So first, we're gonna take the union over all the dimensions. And then for each dimension I, we're gonna take a union of all the components.
You mean K of I, right?
Yes, thank you. So we'll call this x21, x22, x11, 2. And this is called an irreducible decomposition. Of the variety X. How should we represent this variety on a computer from the point of view of numerical algebraic geometry?
Be a product.
So if you wanted to write down equations for this union and you knew equations for each component, then you would be able to do that via your first homework. But the task is not to write down equations. In fact, in many ways, the task of this whole course is to get away from our dependency on equations. Get away from the idea that the only way to compute with varieties is through the algebra. And get on board with the idea that we can compute with the geometry instead. And candidates. So we have the idea of a witness set for an equidimensional variety. What happens when our variety is not equidimensional?
You get different types of witness sets, I guess. Different with different complementary dimension, I suppose.
Sure. So I can write down a witness set. For each dimensional component. So let's call all of this the union of, please, just xi. I could represent this variety simply by representing every equidimensional part of the variety. I can't do it all at once because I'm going to need different L's. That's one reason I can't do it all at once. Right? So I think last week, or maybe it was 2 weeks ago at this point, we discussed how to go from a witness set for a possibly reducible equidimensional variety to a witness set for each of its irreducible components. So in other words, somebody hands me, say, W2. So it looks like those F's, maybe, and some line. So let's say V, L1 and L2 for a couple of random linear forms. And let's say, yeah, just some collection of points. Okay. Call that L1. Okay, so I got 4 points over here on this component, 2 points on that component. How do I tell on a computer which points go on which components? Because what I really like to do is write this where each of these is a witness set for each of the corresponding components. How do I do it?
Well, this might be a stupid idea, but the components should be path connected. So maybe work with the monodromy. So, okay.
That's exactly what we did. And it was called the monodromy breakup algorithm. You have, say, these 6 solutions. You have a way to move those solutions around via homotopy continuation. So you whip that line around and you come back and you see what permutations you get. And as you keep doing this, you keep on refining the orbits of the monodromy group. And you see that, like, yeah, these 4 are able to permute amongst each other, and these 2 are able to permute amongst each other. So these 4 belong to one component, these 2 belong to another. Okay. And if you really want to be sure, you could check all possible traces, and do the trace test a bunch as well. But that's combinatorially expensive, whereas this geometric idea is fairly cheap. This was called monodromy breakup. Any questions? Okay, I still haven't told you though how to actually get a witness set for all of these dimensional parts. Now, one big reason why we don't know this yet is because we actually don't know how to handle non-square systems. So that's where today's lecture kind of begins. The goal is a witness set for every irreducible component of X. And we'll describe a naive way of doing so today. And then if we have time and if there's enough interest, we'll do a updated version, which is much better, called the cascade algorithm. But for today, let's just aim on computing this at all. Okay. So W naught we really want a set of witness sets for every irreducible component. Doing so gives us a numerical irreducible decomposition. And this, toward the end of the course now, is how you represent a variety on a computer. You started with 0-dimensional varieties, you represent them by listing all of them as numerical approximations. Positive dimensional varieties that are equidimensional, you do a slice, you list all the intersection points of that slice. If you'd like, you can decompose it into components using your monodromy breakup. If you have a many different dimensional variety, this is how you do it, and it's called a numerical irreducible decomposition. So what do we have to do? We have some variety. Okay, and yeah, let's say it looks like B of F1. How do we possibly get our hands? Oh, great. On a numerically reducible decomposition. So since we know how to handle equidimensional witness sets, all we really need to do is get our hands on those, because then we can do monodromy breakup on each of them. I printed off the wrong notes, so I've got to pull up the notes. Apologies, it's okay. Thanks. No worries. Okay, so first things first is we need to understand how to handle squaring up this system, because everything we know how to do, we only know how to do in the context of square systems. Sorry, Michelle, you said you did print it out. I will actually take that. Thank you so much. Appreciate it. Oh, it's not the updated version.
It's whatever was supposed to be.
Yeah, so it hasn't gotten updated yet. Sorry. Okay, great. So the first thing to note from an algebraic geometry point of view is that each Fi cuts down the solution set by at most one dimension, with the exception that it may result in no solutions. So this is exactly how linear spaces work, for example. If you have like K hyperplanes, well, the first hyperplane is going to cut down your solution set by at most one dimension, right? Maybe your linear form is just the zero linear form, in which case it doesn't cut down the dimension at all, right? Okay, so now you have one hyperplane, say in 3-dimensional space, and you intersect it with another hyperplane. Okay. Now, if you choose the exact same hyperplane, you haven't cut down the dimension. Right? Probably you will cut down the dimension by exactly one. But then there's this one funny case where you actually do a parallel hyperplane and you cut out nothing. But you're never going to cut out a point with two hyperplanes in 3 space. Okay. So keep in mind that that's what's going on here too. And so that means every component of X has codimension at most M. So dimension at least n minus. I cannot cut out a point in the plane with just one equation. over the complex numbers. All right. Well, what's our goal? X, just as before, some union. One X. For the purpose of this course, we are ignoring the non-reduced components. There are ways to handle non-reduced components, but we're not going to. So recall that being a reduced component of a variety isn't really a definition. Being a reduced component of a variety with respect to some defining equations is a definition. Okay, what it means is that at a generic point of the component, if you evaluate the Jacobian of the system there, you get the expected rank, which is the codimension of the variety. Okay. So that's our definition of being a reduced component of a variety with respect to some defining equations. Okay. So this decomposition is not a decomposition in terms of the variety, it's a decomposition of the variety in terms of the equations. Okay, if you give me different equations, this decomposition is going to change. Even though maybe the variety is the exact same. But we want witness points for the xi, which are the reduced I-dimensional parts. Idea. Solve this. That's my. So if I want to find isolated points of the intersection of xi with a complementary dimensional linear space, that means I need to slice with an n minus I dimensional space. Linear space.
So could you repeat that again?
Yeah, so I want the I-dimensional part. Okay. Let's say I want the one-dimensional part here in this picture. That means I need to slice with a linear space and find the isolated points of that intersection. Right, so that means I need to slice with, say, a hyperplane here and find the isolated points. So what happens when I slice with a hyperplane? I'll get isolated points on the curves. That's the part I want.
Yeah.
The hyperplanes will intersect the higher dimensional things
In curves.
in non-isolated points, curves, and it'll miss the points entirely. Okay, so that's what happens. You slice at dimension I, any components of higher dimension induce positive dimensional solution sets. Anything of lower dimension get missed. Okay. Similarly, if I did it with a line, I would get components I like. There's nothing of higher dimension. The curves and the points get missed. So that's the idea. So if I want curves which are dimension 1, I have to slice with hyperplanes which are dimension 2, i.e. n minus I.
Mm.
But hyperplanes, so a linear space of codimension I is cut out by I linear forms. So the n minus I kind of gobbles itself up twice, and you end up having to slice with the 0 sets of I linear forms when you're dealing with a variety of dimension I.
In other words, you make a square system. But
Oh yeah, that's the problem. This isn't square.
but you have like m I dimension for
This is n plus I equations.
right.
N variables. Why is m plus I greater than or equal to n? Because of this fact. Right?
So m minus-
So the smallest dimension I could possibly cut out. So in other words, the smallest I could possibly be is n minus m. If I plug that in, that's m plus n minus m with n. And that's a lower bound on the dimension of a component. So this left-hand side for any other I is just gonna get bigger. Okay. In fact, I'm only getting equality if I have components, if I'm looking at the component of dimension n minus m. The expected dimension. It's the only time I have equality. Otherwise, this idea naturally lends itself, no matter what, to an overdetermined system. And that's a problem. Somebody remind me why overdetermined systems are bad for us?
That's good.
Yeah, so being overdetermined means it's not square, and not being square is a problem because I mean, think about homotopy continuation. How does homotopy continuation work? At some point, I'm taking a Jacobian.
Yep. That fails, yeah.
That better be a square matrix if I'm going to take its inverse, right? Euler's method and Newton's method both rely on the inverse of the Jacobian. Okay, so I want some system where the Jacobian is one invertible, and in particular, that better be a square matrix. Okay. Overdetermined, sad. It makes me sad, and I've been avoiding it the whole course. So it's time to not. Yeah. So this is the silly solution is like, oh, we're just gonna make it square, right? So somewhere in one of the first classes, I think Jacob mentioned writing our system of equations as a vector of polynomials. So this is gonna be a good idea at this point, because if I'm looking for the I-dimensional part, then I expect that to be cut out by n minus I equations, but it's really cut out by m. And so if this is just a random n minus I by m matrix over C, then this ends up becoming, say, some G1 to Gn minus n. Okay, so let's take a beat and look at this. Okay. Suppose we have 3 equations in 3 variables, and it cuts this out. Okay. And I want to look at the curvy part. So not the surfacey part, not the point part, but the curvy part. So the one-dimensional part. Well, the one dimensions, I expect to be cut out by two equations, because the codimension is 2. 1 hypersurface, 2 curve. So I really want 2 equations, not 3. Okay, so I do this, and what I get is f1 plus 2f2 plus 3f3, 4f1 plus 7f2. Now I do have 2 equations. Okay, but wait, like you've definitely changed the variety, right? Like I must have changed the variety by doing this. Yes, but not by a disastrous amount. Okay. In fact, we actually saw this in our first week when I gave the example of this twisted cubic. I said these 3 equations, no 2 of them can cut out this this variety. I gave you an example. It's in our first lecture. Okay. And what happened is if I tried to take subsets of the equations, I would cut out the variety I wanted, but just extra components too. So my claim is that these curves are still contained in the variety here. Well, why is that? So if I have a point here, P, that means f1 of P is 0, f2 of P is 0, and f3 of P is 0. Okay, well, let's plug it in here. What's G1 of P? Well, it's f1 of P, 0, plus 2f2 of P, 0, plus 3f3 of P, 0. Okay, so by doing this 2 random linear combinations, I still have at least the curves as a subvariety.
Why random? Like you could look at a row echelon, reduced row echelon form, maybe get something like 1 0 0 1 and 0 0.
Yeah, so we'll get to why random in a little bit.
Okay, well, this is a good idea.
So this is called squaring it up. Okay, that's a technical. That's in the literature. It's called squaring it up. You can drop the G on squaring if you'd like. You have my permission. Okay, great. All right, so now we need some facts about how this has screwed things up or not screwed things up. That's still our goal. Our first step so consider this variety instead. Okay, and now we list some facts. Components of V of F dimension greater than I are the same as those of the randomized system of dimension greater than I. Okay, so when I randomize this to try to cut out these curves, this first part says the 0 set here still has the sphere and this funky surface as its 2-dimensional components, because that's bigger than the dimension I'm looking at, and so those components aren't going to change. Use I-dimensional components of V of F, i.e. the ones I care about, are reduced I-dimensional components of V of lambda. The I just indicates the size, by the way. The converse is false. Okay, so this is the price we're paying so far. Up until this point, it seems like randomization didn't hurt us at all. Okay. So it has hurt us. So sure, the really high dimensional components aren't changing, great. But the ones in the dimension we care about, we keep the ones we care about, but we might include extras. Right? Reduced components of B and F are reduced components lambda I F. Non-reduced of B and F non-reduced still a dimension consideration here. Yeah, reduced components in dimension I are still reduced components of this, non-reduced are still non-reduced. But, and we haven't discussed this, but you should know that there's some multiplicity. This may increase.
Mm.
Okay. So being reduced means a generic point has the expected rank of the Jacobian with respect to the system you care about. And in particular, that means that when you solve for a linear slice through a generic point, that point is a regular solution of the homotopy. Okay. I.e. adding a bunch of random linear forms beefs up the Jacobian's rank until its Jacobian is a full rank n by n matrix. Okay. Otherwise, if you're rank deficient, then we saw that this means you're not a regular solution of the homotopy, which means one of two things. One, there's multiplicity. You have multiple paths going to the same endpoint. That is the first way you can have a Jacobian drop rank. Two, the endpoint lands on a positive dimensional component. So this was in your homework, right? So it's another piece of the problematic end game behavior in homotopies in many variables. Okay, the number of points approaching can be thought of as some sort of multiplicity, and you should know that if you square up a system in this way, you will screw with the multiplicity just a little bit, but you won't if that multiplicity is 1, i.e. it's reduced. So if you restrict your attention to the reduced components, the only price you've paid here is that you may have included more components, which may or may not be reduced. So if I square things up, I'm gonna do my best to erase this line. Because what I'm really interested in is drawing in red. This picture in red describes the zero set of the G's. So I have all of the top dimensional components with nothing added. In the component, in the dimension I'm looking at, I have the components I care about, which are still reduced. So they still don't have any, they have multiplicity of 1. But I may include, okay, there's a parabola hanging out in space, and then there's a little piece of string, and let's say that multiplicity is 2. Whatever that is, it's not used. So that is what the G's might cut out. It's not seeing any of the points, by the way. Why? There's only 2 equations. You can't cut out points. However, the points should be a subvariety still, so that just means, the actual picture should look like this or something. Just means those points are on other components. Okay. Great. Oh, I gotta speed this along, sorry. So B of lambda I F looks like. Well, I have the union from J equals I plus 1 and of, and then the union of the X of J, that's an I, J equals 1 to K I. Okay, so these are the big components above the dimension I'm looking at. Okay, then I have the stuff I care about. X, I. I should use something different than I here. I hat. It's gotta be that. This is an actual I. Remember, over here, the left-hand side depends on I, so I can't use I as an index, so I'm using I hat here. Okay. Union, okay, this stuff is stuff I hated anyway. It's like stuff with some multiplicity, it's not reduced. Union, I'll have a bunch of Y, the union of a bunch of Yij's for J going from 1 to say I hat. So these are new reduced components that are included when I square things up. And then I'll do a Z hat. Okay, so big, who cares? I want these. Don't want these. This, by the way, all of this belongs to X, but it's minus the smaller dimensional components. Here is the price I pay. So that's the price I pay in the reduced sense. So these are reduced components of the new system. This is the price I pay with the non-reduced sense. Okay. So now I can do the solving of this. And let's think about what happens to these homotopy paths. Okay. So I could do like a total degree. Try solving the square system, by the way. So try, for example, with total degree. Homotopy continuation will compute every isolated solution to your system, which is reduced. So every regular solution gets hit by this, which means 1. All points. Give this a name, call it out. Of L intersect X, I get hit. We will have all the points we want at the end of the day. That is what this says. As do the L intersect Yij's. Points of L intersect Z or L intersect. Let's call we need a name for this X big. X big. This is X big. Or L intersect X big or L intersect Z hat are very recognizable. So any points land there I evaluate the Jacobian of the system, I notice that it has numerical rank deficiency, and I throw those away, that's junk. Okay? And the only thing I have to do then is differentiate between my 1 points and my 2 points. Okay? Okay, so ready, let's do this. So we have now a hyperplane. Okay. It's intersecting twice there. Or there, point there, 1, 2, 3 there. Couple points here. Couple points here. Maybe a bunch of points, I don't know, there. And then like, oh, it's a sphere, so it's intersecting there. Okay, so that's what's going on. Okay, and if you do a homotopy from a square total degree start system, which only has points, right? You can actually see the points flying around the three-dimensional space, and they'll land here, here, somewhere on this curve, here, 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 somewhere here, maybe a bunch of times here, I don't know. Okay, and maybe a bunch of times here. So that's what I'm gonna get as the output of my homotopy continuation. I immediately throw out anything here because the Jacobian's dropping rank, because it lives on a positive dimensional solution set. These are points that lie on a curve instead of being isolated like these. Same with everything here. So those all get thrown out. Okay. And I'm left with these 3 points in this point, which I do like. And these 2 points and these like 40 points or something that I don't like, because they actually correspond to new components that got introduced in the squaring up system. How do I tell what got introduced in the squaring up system?
You could change the matrix.
Exactly. So you could just change the matrix. That's one option. And that will change which components are getting introduced. Right? And then you can recognize things that way. Or you can use Depok's method and just evaluate your system.
Yeah.
If you like. Okay. In reality, probably evaluating your system is going to be good enough. But if you really would like to be careful, just consider these points as the witness points for the components you care about and the others. Do a new randomization. You'll get the points you care about again, and some others. And then check which components are in common. And we know how to do that via witness sets, because we have variety containment algorithms. Yes.
Question. When does this, so does this work for any random matrix I pick, or are there, say, some forbidden matrices that I should not use here?
There are forbidden matrices you should not use.
Okay.
I don't have an example off the top of my head. But indeed there. Yeah, thank you,
definitely.
Michelle. Perfect. Yes. Yeah, don't use the zero matrix. It's gonna be bad news. But full rank matrix, I still think there are instances where you run into issues. Yeah, but even if you are full rank, I think you're still gonna be in
So for
bad.
instance, a column is 0.
Yeah, that would be the same thing as just choosing subset of the equations. Okay, good. So that's the idea. And now we know how to get the isolated points for the I-dimensional part, the one-dimensional part. Okay, square it up, solve it like you would normally solve it, throw out anything with a bad rank at the end, throw out all the singular endpoints, all the endpoints that lie on positive dimensional components, and then check which points shouldn't have even been invited to the party at all because they don't solve the system. Okay. Now you got these, and you have a square system which allows you to move them around. In other words, you have a witness set, right? Albeit you need lambdas in front of these f's now. You need this all to be square to have the ability to move things around. Or at some point, you may find yourself detaching from the idea of the witness set being a triple and start really thinking about it as an abstract concept of a witness set is a way to represent points in a slice and move them around. Okay, in which case I'm clearly giving you a way to do that. And now how do you distinguish these 3 points from that one? Monitor may break up, just like before. Okay. Make sense? Okay. So the problem with this is it's super duper inefficient. Okay. It's super inefficient because when you square this up and you take random linear combinations, what is the degree of the first G1? It's the maximum of the degrees of F1, F2, and F3. Okay, but what if like F1 has degree 100 and these two are like have degree 2 or something? I don't want to be intersecting something of degree 100, something of degree 2, something of degree 2 sounds a lot less difficult than intersecting like 2 things of degree 100, right? In particular, my Bezier-Buttons gonna jump. Okay, so there's a new algorithm called, well, maybe not that new at this point, but there's a cascade algorithm which considers the process of computing a numerically irreducible decomposition, not in steps kind of done sequentially after one another, but as one big problem. Okay, so it kind of puts all this information into one packet. But geometrically, it's a little bit more difficult to understand, and I've yet to decide whether or not I'm going to include that in the course, because this is sufficient, at least from the theoretical point of view, that one can compute a numerically irreducible decomposition for the reduced part of any variety. Okay. Okay. Let me yeah, we got through everything. That's a miracle. Okay, great. Thank you very much. I will see you Thursday. And we will continue with witness sets, potentially doing the cascade algorithm, potentially not. And then next week, which is the last week, we will cover certification method. So how do you get mathematical proofs from your numerical computations? So that'll be super exciting. The last day of class then is next Thursday, and that is when the project, final projects will be due.